Welcome to the screencast for Chapter 4 from Brown and LeMay on aqueous reactions and solution stoichiometry. First, some definitions. Remember that the substance present in the greater quantity is the solvent. The substance present in the smallest quantity would be the solute, and then together they're going to make up the solution. And so you might remember from last year I said you could kind of think of it as saying that you take the solute plus the solvent and you make the solution. And of course the solute is a small word, and then you have your medium-sized word here, the solvent, and then together they make the biggest word, the solution. And some more definitions. An electrolyte is a substance whose aqueous solution contains ions, right? So here we have the electrolyte, right? So that's the word, electrolyte, and here's the non-electrolyte. So next to that we have an acid, which is then broken down into a hydrogen ion and a cyanide ion. And so when we put these in water, these are the ions we get, and so therefore that makes it an electrolyte. If a substance does not dissolve in water and does not dissociate, then it's generally referred to as a non-electrolyte. And of course the word dissociate means that they're going to separate, right? And this is what ionic solids do when you place them in water. As an ionic compound dissolves, the ions become surrounded by water molecules. That's referred to as solvation. So those are your terms on this page. Then we have also the idea that molecular compounds are non-electrolytes and do not dissolve in water. There are some exceptions to that, though. Acids are the notable exception. They are molecular compounds, but they do dissolve in water, as shown here with the hydrocyanic acid dissolving into hydrogen ion and cyanide ion. The second example on this page is an ionic compound that is also a base. And so you have ammonium hydroxide producing ammonium ion and hydroxide ion. And finally, a plain old ionic compound, mercuric chloride producing mercuric ion and chloride ions. Just to be clear, the word dissociate does not mean the same thing as dissolve. Remember that some substances will dissolve just a little tiny bit, and so therefore we don't say that they dissociate very much, but they will dissolve in water. They just don't dissociate into their ions. And so a non-electrolyte actually can dissolve in water, but then does not dissociate. Remind me to clarify that in class if you're still confused. All right, this slide is showing on the left side here we have a compound with a high solubility. So notice that we have green and purple little circles all completely dissociated. Next to that, low compound solubility, there's a big clump of them at the bottom and just one green, one purple little dot here. So it indicated that not much of it dissociated and therefore not much of it dissolved. Over here we have the idea of a strong electrolyte where all of the ions have been separated, so you see pluses and minuses. Over here we have a few of them separated, so that's going to be your weak electrolyte. And then over here, no separation of ions, in other words there are no ions present, that's a non-electrolyte. And so that's basically what this slide is referring to. Do keep in mind that, as it says on your handout, a weak electrolyte and a substance that dissociates nearly 100% are not the same thing. For example, acetic acid is soluble in water, so it'd be like this picture here. The acid molecule is staying in acid. It's not dissociating into its ions, but it does dissolve nearly 100%. And so that's the difference between a weak electrolyte and a strong electrolyte. Acetic acid would be your weak electrolyte or non-electrolyte, and the stronger one would be the one that has lots of ions dissociated. One of the things that you'll have to do is to indicate that something is a strong electrolyte by using a single-headed arrow. And so something like hydrochloric acid, for example, would be written like this. You have HCl as the formula, and then AQ, which of course stands for, yes, I know, you know it, aqueous. And you're going to have a single arrow to the right, indicating that it is a strong electrolyte and therefore dissociates nearly 100% into its ions, H plus and Cl minus. Now, if you have something like a weak electrolyte, like acetic acid, then we would see that it would look something like this. There is the formula for the acid, but then the fact that it really does not dissociate a whole lot, so you would see a double arrow. And there's various different types of double arrows, but that's one type. So you would have a little bit of dissociation here, but the double arrow indicating that a lot of it is going to remain as the molecular formula of the acid. So most of the time it's going to be this one. Here we see the insoluble product of a reaction, and we call that a precipitate. So this yellow solid that is forming in the picture here is technically a precipitate. The solubility of a substance at a given temperature is the amount of that substance that can be dissolved in a given quantity of solvent at that temperature. So there's a big word for your solubility. Substances with very low solubility are referred to as insoluble. So one thing you're going to need to work on are the solubility rules for substances. But fortunately for you, you won't have to know as many as last year's group of students. And so in class we will discuss the ones that you need to know. But the ones that I can think of off the top of my head would be the alkali metals are going to always be soluble ions. So it'd be sodium, potassium in that column. And also always soluble would be nitrates and ammonium, which we just looked at as NH4+. So we will look at the others that you need to know in class. So the next topic here are ion exchange reactions, which last year we referred to as, or some of them as, double replacement reactions. There's also another fancy name, they're called metathesis reactions. In order for this type of reaction to occur, one of the following things has to happen. So one would be a precipitate forming. So that could very often be a double replacement type reaction. A gas is generated, again that could be double replacement. A weak electrolyte is formed, or a non-electrolyte is formed. So all these are examples of, or could be, double replacement reactions. And here you see an example of a double replacement reaction where we're combining barium chloride and magnesium sulfate, and we get barium sulfate and magnesium chloride. Note here that at the bottom we now have what is called the complete ionic equation, where the substances that are dissolved in water are shown as dissociated. And so you have Ba2 plus 2 chlorine ions plus magnesium 2 plus the sulfate ion. So these are all ions over here. On this side, this is the precipitate, the barium sulfate, that is not shown as dissociated. The magnesium, though, is still an ion, still dissociated with the 2 chlorine ions over here as well. Okay, time to practice. So on page 129, question A, we have, what compound precipitates when solutions of Fe2SO4 and LiOH are mixed? So you can answer this in a couple of different ways, but one way, of course, would be to write the equation. So we have Fe2SO4 plus LiOH. All right, and what are we going to make when we combine those? Well, first of all, we would notice that these are going to be solutions, which is what it says in the equation, the problem. So you'd have AQ after each of those. And then the substances that are produced are Li2SO4. Oh, Mrs. Kovacs, why are you writing Li2SO4? Well, remember we'd have to look up what sulfate's charge is on the polyatomic ion list. Sulfate is -2. Lithium is +1 because it's in column 1. Remember this? And so then you would write Li2SO4. Now the other thing I'd need to look at is the solubility rules, or I'd need to remember that lithium ions are always going to be soluble, no matter what they're combined with, so that means that this compound has to also be aqueous. Now the other compound that is produced would have to be whatever's left over, and so that's going to be your iron and your hydroxide. Now what is the charge on the iron on the left-hand side? Well, if you look at the formula, you have Fe2SO43. If we kind of do a reverse crisscross there, you would realize that iron is +3, and so the formula on the right-hand side here has to be FeOH3, which I'm barely going to fit on this page. Now that would have to be the precipitate because the lithium sulfate is aqueous, so whatever's left over is going to have to be your precipitate, marked with an S, which stands for solid. So there's the solution to part A. All right, now how about part B? Well, it says write a balanced equation for the reaction. Oh, okay, we're halfway there. So we have the balanced equation. We have the equation. We need to balance it now. And so everybody take a minute to do that. Pause the recording, and then turn me back on. Okay, we're back. So how would you balance this thing? Well, it should be a 6 here, and then it should be a 3 here, and a 2 over here. Technically a 1 on the iron sulfate there. All right, and continuing on, letter C. Will a precipitate form when solutions of barium nitrate and KOH are formed? Are mixed. So we have barium nitrate plus, I lost my place, sorry, plus KOH, right? So then you would say, well, all right, so one thing would be potassium nitrates, that's KNO3. Is that aqueous or is that a solid? Well, that's got to be aqueous because it's got potassium in it. And then the other one would have to be the barium nitrate. Barium hydroxide. And you could say, oh, well, I thought hydroxides were solids most of the time. Well, yes, they are, except when you have something from the second column, which makes this substance a strong base. Barium hydroxide is a strong base, so that would be aqueous. And remember that on this side, these were solutions, so they're going to be aqueous. And so this reaction does not occur because all of the substances are aqueous. And remember that that was part C. Balancing the equation was B. Cool. Let's go on. All right, so we just looked at a complete ionic equation, which shows all the substances in ionic form. If the ion appears on both sides in exactly the same form, it's called a spectator ion. If we take out the spectator ions, what's left is called the net ionic equation and shows us only what is actually reacting. If all the ions are spectators, then no reaction occurs, which is just like the problem we were just looking at. So now let's take a look at the practice exercise on page 130. All right, and so on page 130, we have what looks to be silver nitrate and potassium phosphate. And it says, I'm on page 132, so 130, write the net ionic equation for the precipitation reaction that occurs when aqueous solutions of silver nitrate and potassium phosphate are mixed. So we're going to write, everybody stop the recording and try this, and then turn me back on and see if you got it right. Okay, we're back. So silver nitrate plus potassium phosphate yields silver phosphate plus potassium nitrate. All right, so what can you tell me about the solubility rule here? Well, potassium nitrate contains potassium. What do we know about potassium? It's always soluble, so that's going to be AQ. So if that one is aqueous, and we're pretty sure that this precipitates, then that means that the silver phosphate is going to have to be your precipitate. And what did the question say? Write the net ionic. Okay, so now what do we do? Well, you might remember also from last year that the little shortcut for writing the net ionic was to take and write the formula for the precipitate, because that is certainly what is the product of this particular reaction. And then the things that are coming together to form that are really just going to be your silver ions, which are aqueous, plus your phosphate ion, which is also aqueous. Okay, so there is the net ionic equation for this reaction. Remember that the spectators would then be the potassium ion and the nitrate ion. All right, talking a little bit more about acids in detail, we want to note that acids form hydrogen ions when placed in water that are going to look like that, right? Hydrogen ion. They have a sour taste. A hydrogen ion is simply a proton. It's lost its electron, so therefore it's just a proton. So that's why acids are often referred to as proton donors. Very helpful definition of an acid. If there's only one hydrogen ion, it's monoprotic. If there's two, it's diprotic. If there's more than two, we say polyprotic, usually. And let's give some time to bases. Bases react with hydrogen ions. They have a bitter taste. They produce hydroxide ions when you place them in water. However, some of them do not produce hydroxide. That would be ammonia or the amines. And so these two pictures, on the left you see ammonia, right, NH3, with the lone pair of electrons up there. And then this diagram is of an amine. So what has happened to the third hydrogen? Well, now it's an R. Is R the symbol for an element? No, R is the symbol for a group of atoms of some number and some kind. So it's just a way to abbreviate this as a group of atoms. That makes this side, or this compound formula, an amine, and this one with the 3 hydrogens is ammonia. Alright, here's an important slide with lots of information. Strong acids and bases are strong electrolytes. Weak acids and bases are weak electrolytes. The reactivity of an acid can depend on the anion, so go ahead and read that information. You should also memorize the list of strong acids and bases. You're going to need to know them. And then we have strong electrolytes, include strong acids, strong bases, and all ionic compounds. Weak electrolytes, weak acids, and weak bases. Non-electrolytes, most molecular substances. All right, let's take a look at sample exercise 4.6. The formula, the first one is CaCl2, and it would like us to classify these as strong, weak, or non-electrolytes. This is a strong electrolyte because it is an ionic compound. HNO3 is strong because it is a strong acid. C2H5OH. Well, is that ionic? Nope. So it's not a strong electrolyte. So you might say, well, is it a weak electrolyte? Well, that means it would have to dissociate. And this particular compound is classified as molecular, so that makes it a non-electrolyte because it does not dissociate, right? So no dissociation. Then we have HCHO2. Well, what do you think about that? Well, it's got an H on the front, and so this H is an acidic hydrogen, which means that it will produce H plus to some extent, plus the rest of the compound. And so this one is classified as a weak electrolyte. And finally we have KOH. Well, that's an ionic compound, which makes it strong, but it's also a base, and it's a strong base, which makes it strong. So you try practice exercise on page 134, and we'll take a look at that in class. Well, neutralization occurs when acids and bases are mixed. A salt is an ionic compound whose cation comes from the base and whose anion comes from an acid. So if we have calcium sulfate, the calcium comes from the base calcium hydroxide, and the sulfate comes from the acid H2SO4. So if we've combined these two compounds, then we will get calcium sulfate plus, oh, it's neutralization. What does that mean you probably form? Oh yeah, water. And so water is always a product when you combine these. If we combine a strong acid with a strong base, we're always going to end up with the net ionic equation showing only hydrogen ions and hydroxide ions. And so you can see that from the first equation. If we balanced this, we would need, let's see, a 2 over here in front of the water. And so then you'd end up with 2 waters. And if we dissociated this, you'd have calcium ions, hydroxide ions, hydrogen ions, sulfate ions, more calcium ions, more sulfate ions, and water, written as H2O. So it would technically be this to begin with, right? And then we could delete the 2's again, because that would, a balanced equation would reduce the coefficients there. So remember that the calcium and the sulfate would then become spectator ions. Here's some more practice, but I think I'm going to have to stop this video. It's going a little long. So work on these on your own, and we'll go over them in class.